Okay, so I'm pleased today to present my recent research work, which is part of my thesis in the Laboratory of Meteorology Dynamic in France, in Palaiseau, of École Polytechnique. So the thesis is in relation with renewable energy, specifically the response of the Moroccan electricity mix to the integration of two solar technology, which are PV and CSP. So I will be discussing the impact of cost and storage. So let's get started. So first, I will present the specific situation of Morocco, which can be considered as the main motivation of this study, the research gap of the solar technologies, and the main research question that this study aims to answer. Then I will present our objectives, the methodology adapted and the data sources. Then I will present the results, the model results for various renewable penetration and technology combination, and discuss the role of CSP and storage in electricity system adequacy. Then I will give the main findings and give an overview of my ongoing research work. So as I said, there are two types of solar technologies that may replace fossil fuels to meet the world's future energy needs. PV, which does not use the heat to generate electricity, but instead it uses the sunlight through the photoelectric effect to generate the direct current that is converted to alternative current using an inverter, and CSP that use mirror that concentrate solar radiation by tracking the sun throughout the day, and then they focus this solar irradiation onto a receiver that contains oil or water that once receives solar irradiation, it is transformed to steam that is then used to operate turbine that is connected to electricity generating generator. And if there is an excess of steam that is produced from the solar field, it is stored in thermal energy storage system for later use, and the number of hour of production from this thermal energy stored is it depends. It is proportional to the solar multiple, which is the size of the solar field compared to the electricity generating turbine. So Morocco, as one of the MENA region, has considerable, has favorable condition for not only solar energy, but also for wind energy. Currently, a number of plants are being built or planned or connected to the grid, particularly CSP with storage and hybrid PV and CSP with thermal storage. Currently, 34% of the Moroccan electricity needs are covered by renewable energy, and Morocco aims to increase this fraction to 42% by 2021, with equal proportion between hydro, wind, and solar, so 14% for each source. And Morocco aims that 52% of the national demand should be satisfied by renewable, where 20% should come from solar, 20% from wind, and 12% from hydro. But the optimal proportion between PV and CSP, and also the amount of storage associated with CSP, are not clearly defined within this strategy. So the question that arises in this context is that renewable deployment is good to reduce CO2 emission, to reduce the energy dependency, and also to solve the problem of peak demand. But it's difficult to convince an investor to invest in specific renewable technology because we can produce renewable energy from different sources, from wind, from PV, from CSP, but each technology has its own characteristic, specifically between solar technology, PV, and CSP. First, in terms of cost, PV is cheap, and further cost reduction are expected in the future, while CSP is recently developed, so it still has high initial cost and requires policy mechanism to lower the investment cost. Another point is that the battery, which is in general deployed with PV, is expensive and can only cover some daytime needs. However, the thermal storage, which is combined with CSP, can cover several hours after sunset, and it is cheap. The second difference between PV and CSP is the resource used for production. For PV, all the components of solar radiation are useful for the PV production, even the diffuse one. However, for CSP, it requires higher direct normal irradiation, so very specific location with clear atmospheric condition to be economic. So PV tends to be less variable than CSP because it is less sensitive to clouds, for example, than CSP. So PV can be also be installed everywhere, while CSP require large capacities, which tends and sometimes in very far location that tends to be far away from consumption seats. The third aspect is the correlation of PV and CSP production with demand. So what we can see here is the heat map shows in abscissa the yearly cycle, and in ordinates the daily cycle, so the hours of the day of the demand in color bar. What we can see is that the demand is high during summer in Morocco due to air conditioning use. And there are two peaks, two daily peaks, one in midday and second in the evening. If we do the same thing for the PV, CSP without storage and CSP with storage capacity factors, what we can see is that PV can only contribute to some midday loads, and its production drop during summer because PV panels efficiency is more sensitive to high temperature than CSP. We can see here that they have the same profile, but the advantage of CSP over PV is that it has a positive correlation with the Moroccan seasonal demand, because more the temperature is high, more the CSP efficiency increase. CSP with storage can produce at any time because it can charge and discharge more frequently. So it can be solution first to situation where we can have shortage of energy, and it can also be solution for situation where we have curtailment from PV and wind, because it can be shut down during their maximum production. So it is it can works better to adjust with demand and electricity prices than PV or wind. And it can also replace baseload generation, so it can fulfill the greenhouse gas mitigation targets. So this difference between solar technology should be counted when designing an optimal prospective power supply mix based on renewable technology. So in this study, we show how the cost and storage affects the penetration and the variability of these two technologies in the Moroccan electricity mix. We see if the fact of taking into account correlation between technology and region reduce the variability of renewable energy. If the storage can reduce the main renewable integration challenges, it means that if storage can increase the capacity credit, reduce the mid and base load, reduce the situation of shortage or surplus of electricity production. So existing research tends to focus more on mixes based on PV and wind, and to some extent to CSP with storage, but their objective is either maximizing or minimizing the cost or minimizing the variability. But there is no study that aims to increase the penetration and at the same time the variability and minimizing the variability and the cost. So our objective is not only to provide adequacy services to the electricity system by reducing the variability of the total production over the national demand, but also to maximize the renewable production, which is constrained to not exceed the total cost of the actual renewable capacity installed in Morocco in 2018. So this optimization, this mean variance optimization problem is implemented in the E4CLIM model, which we consider for Morocco that he has no exchange with other countries and no network constraints. And so from the geographical and climate data, we compute the regional electricity consumption, which is fitted to observation by taking into account the economic activity and the sensitivity of the demand to temperature. We compute the hourly PV capacity factor with and without storage based on a parametric approach that takes into account the sensitivity of PV panel efficiency to temperature. We compute also the wind capacity factor using power curve after the extrapolation of the wind speed at hub height, and the CSP with and without storage. So our strategy is to be able to produce at nominal capacity all the time by taking into account or not the constraint on storage. So once the all capacity factor of each technology is computed at each climate grid point, they are summed over zones and corrected against observation. And then we optimize the technological and geographical renewable capacities by maximizing the renewable penetration and minimizing the variability while satisfying the total cost constraints. Here, the risk, as it is defined as the variance of the total production with respect to the national demand, it does not take into account the specific timing of fluctuation of the production compared to the demand. So that's why we introduce some residual low duration curve diagnostics after the optimization steps to give an idea of the general services that can be provided by each technology. So first, we convert the demand time series to low duration curve by sorting the demand from the highest to lowest value. And then we plot the residual low duration curve, which is the same as the low duration curve, but it is now the demand minus the total renewable production. And we illustrate the contribution of each technology to reduction of different load bands by dividing the low duration curve into 3 intervals. And we see the contribution of each technology in reducing the peak load, so in increasing the capacity credit, in reducing the mid load, and in reducing the base load. And we can calculate also the energy required or the capacity required from conventional and the energy that is curtailed over 1 year. So before this residual low duration curve diagnostics, we compute the solution of the optimization problem, which is not one optimal mix, so not one point, but Pareto efficiency, where all the points are optimal. So here we represent the mean penetration as function of the variability or the risk of not satisfying the demand. We have different frontier. The blue is for the global strategy, means that the mix takes into account correlation between technology and region, and we aim to minimize the variability of the total production over the total demand. The same is for the black line, but without the total cost constraint. And here is for the mixes for the technology strategy, means the mix that takes into account correlation between technology for the same region. And here is the mixes for the base strategy where all the correlation are ignored. For the tree frontier, the total cost constraint is not activated, but here we take into account, in the blue line, we take into account the total cost constraint. The gray area means the not feasible solution, and the white area is suboptimal solution, suboptimal mixes. So we represent also different scenario mix. The gray cross is the actual Moroccan mix, and the mix with the same penetration as the actual but with lower variability is in blue triangle. The mix with higher penetration but with the same risk is in blue hexagon. The mix with the largest penetration before the activation of the constraint, so before the divergence between the global constraint and unconstrained frontier, is in black dots, and the mix where the cost constraint is activated in blue cross, and the mix with the highest penetration in blue square. We can also see the benefits of taking into account correlation between region and technology in reducing the renewable variability by comparing the difference between the global and technology strategy, or the difference between the technology and strategy. So we calculate the ratio between the penetration and variance at each point. For each level of penetration, we represent the wind fraction in blue, the CSP fraction in orange, and the PV fraction in brown. And the stars is the actual fraction installed in Morocco. The vertical lines is equivalent to the black dots, so it's the mix with the largest penetration before the activation of the cost constraint. And due to this maximum cost constraint, we identify three regimes. The first regime is where only the variance that plays a role. So the technology that maximize with low variability, so that maximize this ratio that is installed. The second regime where the covariance, but also the costs start to play a role. So the technology that minimize this ratio that is installed. And third regime where the technology that represents the best trade-off between the cost and the capacity factor that is installed. So we do that for 6 combination. First, we start by only PV and wind. Then we add CSP without storage. Then we add CSP with storage, and we increase the storage duration. So more the SM is high, the solar multiple is high, more the storage duration is high. So the first thing that we can see is, as long as the constrained global frontier coincide with the unconstrained one, the technology share is constant with the mean penetration for all combination. But at high, they are constant because little capacity is invested to reach low penetration. So we satisfy, we don't exceed the total, the actual total cost, which is the cost constraint. But at high penetration, the constrained frontier start to diverge from the unconstrained one, and the technology fraction are no longer constant with the mean penetration, because we can't increase the penetration and at the same time reduce the variability and of renewable energy and satisfy the cost. So that's why the technology fraction is not constant with the mean penetration at high penetrations. What the second thing that we can see is that at low penetration, wind is introduced first, then followed by PV. And the introduction of CSP without storage does not affect the technology share. Even here, it is introduced at the expense of PV, but we can see that PV remain largely dominant over CSP. But when we introduce the storage, CSP replace completely PV, And more the storage duration increase, more CSP becomes more regular than wind and remove completely PV from the mix. At high penetration, we can see for all combination that wind is dominating the mix, and the PV fraction is decreasing and CSP fraction is 0 for all the combination. This is because the wind and PV has comparable costs, but being much smaller, their cost is much smaller than the cost of CSP. So that's why we introduce more wind and PV. And why the wind is introduced more than PV? This is because even PV has lower costs than wind. This is because the capacity factor of wind is higher and is more regular than PV, which involves less capacity to be installed to achieve high level of penetration. So less investments. So the technology that represents the best trade-off between capacity factor and cost is wind for Morocco. The third thing that we can see is that the difference between the global and technology frontier is large for all the combination, which means that we can reduce the renewable variability strong reduction of variability can be achieved through the regional diversification. So more we take into account correlation between regions, more we have less variability of renewables. But taking into account correlation between technology differs from combination to another. Here the difference is weak. So PV and wind are negatively correlated in Morocco. However, it is large between in the PV wind CSP combination. So here, taking into account correlation between PV and CSP matters to reduce the risk of not covering the load. And more the storage duration increase, more the difference is small. So more we have storage, more we don't need to take correlation between technology and region to reduce the variability. So this results allows us to discuss the actual mix, which is to the right of the optimal frontier, which means that the actual or the current optimal, distribution of technological and geographical distribution of the actual mix is suboptimal, but can be optimal if Morocco increase its level of penetration or reduce the variability. So how Morocco can reduce the variability? If we consider that all the CSP power plants in Morocco are equivalent to SM 1.7, we can see that if Morocco increased the fraction of CSP and increased the fraction of wind and remove completely the PV, its mix can be optimal. So to summarize, we model the optimal recommissioning of the Moroccan electricity mix to analyze the integration of CSP with different storage duration in the mix, how it changed the integration of solar technologies in the mix, making use of regional and technological synergies. So what we found is that the optimal mixes are sensitive to costs at high penetration. And the technologies that with low variability is wind and CSP with storage. And the technology that represents the best trade-off between capacity factors and costs in Morocco at high penetration is wind. We show also that regional diversification is key to reduce the variability, but the technological or the temporal complementarity is only relevant for when PV is integrated with CSP without storage. We show also that if small level of risk and high level of penetration is targeted, investment should be increased, should increase to integrate more CSP with storage, because to take also the benefits of CSP at high penetration, because I didn't present it, but we have found that CSP can reduce the curtailment, can reduce the capacity required from conventional, and contribute better than wind and PV to reduce the peak demand. So this result is or step of my ongoing research is to compare these results to the integration of CSP with storage, but taking into account the constraints on storage and the cost of storage for different storage duration. See also the impact of the integration of PV battery for different inverter loading ratio. So it means different solar panels size. Conduct parametric studies which solar field size and storage capacity can minimize the total cost, the cost of production and the cost of storage, and assess the impact of climate change on the Moroccan electricity mix, and see the flexibility of CSP with storage and PV battery in reducing the climate sensitivity. So this is the reference I have used, and thank you for your attention.